The distances separating the stars are so enormous that it is even difficult to imagine them. Suffice it to say that taking as reference the average separation between the Earth and the Sun, the so-called astronomical unit, AU, equal to 149.6 million kilometers, the distance that separates us from the nearest star, Proxima Centauri, is 266,000 times greater, that is 103 million times the distance from Earth to the Moon. Even a ray of light, which moves at the maximum speed allowed by the known laws of physics, takes 4.2 years to reach us from Proxima Centauri, while less than 8.5 minutes is enough to fill the space that separates us from the Sun. In these numbers, in their relentless inevitability, is enclosed the problem of interstellar travel. If we then take into account the dimensions of our galaxy, about 100,000 light-years in diameter, and those of the observable universe, more than 10 billion light-years, the question of trips in the deep cosmos can only leave us dismayed. Nevertheless, especially since the 50s, several scientists have accepted this exceptional challenge, facing it with great passion and extraordinary inventiveness. Of course, the problems to be solved were and still remain enormous, but there is one thing that not everyone knows. The first interstellar journeys, however rudimentary, have already begun. At this moment, there are space vehicles that have already gone beyond the known boundaries of the solar system. These are the automatic probes launched by NASA for the exploration of giant planets, and thanks to the trajectory chosen for their mission, they have gained enough energy to escape permanently from the gravitational grip of the Sun. The first to leave the Earth in 1972 was Pioneer 10, destined to fly over Jupiter. The last signal received was on January 23, 2003, when it was 80 UA from the Sun. At the moment, it is 122 UA away, and at a speed of 12 kilometers per second, it is heading towards the constellation Taurus. It will pass relatively close to a star in 2 million years, but at that point, it will be only an inert wreck. In the extremely unlikely event that the probe is detected and recovered by an alien civilization, it will tell its story through the famous gold plate on board, designed by Carl Sagan and Frank Drake. The twin Pioneer 11, launched in 1973 to Jupiter and Saturn, ran out of energy at the end of 1995 and has been silent ever since. But it also carries on board the gold plate, and in 4 million years, it will pass in the vicinity of a star of the Eagle constellation. The two other messengers of humanity among the stars are the automatic vehicles Voyager 1 and 2, both launched in the late summer of 1977 to explore the systems of Jupiter and Saturn, and in the case of Voyager 2, also those of Uranus and Neptune. They have brilliantly surpassed all the most optimistic forecasts of their operation, so much to reach and exceed the boundaries of the heliosphere after a journey that lasted tens of years. But even as dead, the two probes will continue their unstoppable journey through the stars, moving away by 3.5 UA per year on Voyager 1 and 3.1 UA per year on Voyager 2. In the remote but always possible eventuality that during their wandering through the galaxy, they will be intercepted and studied by an extraterrestrial spaceship, the two Voyager also carry on board a message of ours, a golden copper disc, 30 centimeters in diameter, containing a phonographic recording of images and sounds, chosen to represent us and our planet. Each disc is housed in an aluminum case together with a reading device. On the case, in pictorial form, as in the Pioneer plates, explanations are given about the nature of the spacecraft and how to decode the information recorded in the disc. But even in this case, the message represents more than anything else our inalienable desire to defy death, entrusting a part of our culture and our world to eternity. At the speed of the Voyager, representative of our current technological capabilities, it would take 76,000 years to reach the nearest star. This duration would be totally incompatible with any reasonable form of interstellar travel currently conceivable. Even using completely autonomous robotic probes, it is difficult to assume that all onboard systems can continue to function for such a long time. But even if this were to become technologically plausible, would we be able to invest the enormous human and material resources necessary for an enterprise that only some of our very distant descendants might enjoy? So the first obstacle to overcome is represented by the enormous distances that separate the stars. This little data is enough to understand that we need technologies completely different from the chemical propulsion used by New Horizons, Cassini, Voyager, and countless other probes to make an interstellar journey in times compatible with human lifespan. Ionic engines like those used in the Deep Space One and Dawn missions are not good either, because they build their acceleration with exasperating slowness. Instead, you need systems capable of accelerating a spacecraft to a significant fraction of the speed of light in no more than a few years. For interstellar travel to become attractive for human beings, triggering that cocktail of aspiration, ambition, curiosity, and competition that motivates our greatest feats, we should significantly increase the speed of travel. An acceptable value could be between 5% and 10% of the speed of light, c, but certain missions could also be conceived and carried out with a speed of just 0.01 c. A possible solution to this problem was proposed in the 70s of the last century by the Daedalus Project. Under the aegis of the British Interplanetary Society from 1973 to 1978, a group of engineers developed the construction schemes of a giant spaceship as tall as a skyscraper, weighing 54,000 tons, to be built in orbit around the Earth. The spaceship, powered by a futuristic nuclear fusion engine, would have been able to reach a final speed of 0.12 c, 36,000 kilometers per second, and to reach, after 46 years of travel, Bernard's star 6 light-years away. Daedalus did not have a human crew. It was expected that after about 25 years from departure, 2 5-meter optical telescopes and 2 20-meter radio telescopes aboard the second stage of the spaceship would start automatically scanning space around Bernard's star, looking for possible planets to photograph and analyze with spectroscopes and other scientific instruments. But the project was too ambitious and expensive, so it never passed from the ideation phase to the realization phase. The technical problems to overcome were immense, starting with the need to obtain large amounts of helium-3, which together with deuterium was the main ingredient of the mixture needed to feed the hypothetical fusion engine. So the project was abandoned, leaving the dream still unfulfilled of the interstellar journey to the following generations. Daedalus was in practice a giant automatic probe, and putting men on board would have been enormously more expensive and complex, involving scales of mass and energy from thousands to millions of times greater. Yet even these scenarios have been explored, up to give birth to the idea of the interstellar arches, gigantic ecologically self-sufficient habitats able to wander for thousands of years among the stars, while countless generations of men, animals, and plants follow one another inside them. In practice, huge space colonies destined to be launched into interstellar space, even at modest speeds less than 0.01 c. Although it may be difficult to imagine why humans should undertake a journey knowing for certain that they would never reach their destination. In any case, in those same years, the American physicist Robert Bussard proposed an original way to solve the problem of the enormous amount of propellant needed to sustain speeds equal to a fraction of the speed of light. Thus was born the concept of the Interstellar Ramjet, a vehicle able to collect during the trip the hydrogen present among the stars to exploit it in a nuclear fusion engine. But apart from the problems presented by the realization of the engine, the collection of interstellar hydrogen would be far from simple. Assuming an average density of 1 atom per cubic centimeter, to collect 1 kilogram of hydrogen traveling at a tenth of the speed of light, it would take a funnel with a mouthpiece of over 5,000 kilometers in diameter, and the collected matter would be negligible compared to propulsion requirements. For this reason, interstellar ramjets in the various versions proposed are not considered physically feasible. The space engineers have then taken another direction, going from the gigantic to the very small, starting to design missions conducted with intelligent robotic probes, miniaturized beyond any limit currently conceivable and able to travel at 0.1 c. In practice, they started to think about the possibility of using the so-called probes of von Neumann, that is to say of automatons that once arrived at destination would be able to build with the available raw materials copies of themselves. Having successfully completed the exploration or colonization of a world, von Neumann's probes could start new automata to other star systems to repeat the enterprise. Fractal colonization of space, therefore. But we must admit that with these scenarios, we are unfortunately more in the field of science fiction than in that of realizable technology. Since then, no great progress has been made. But in the meantime, something has happened that has changed the cards on the table. That is the discovery and precise location of extrasolar planets similar to the Earth around other stars. Almost all the projects we have just described date back to a time when nothing was known about the actual existence of planets around other stars, let alone their physical and orbital data. This certainly did not make it very easy to find attention and economic contributions for those who proposed to build huge and very expensive spaceships and then send them to stars of which we knew practically nothing. It would have been too big a gamble to go blind with such expensive missions, and therefore unrepeatable in case of failure. Things started to change after 2000, however, when in a few years thousands of extrasolar planets were identified, many of them of terrestrial type, and orbiting within the habitable region of the star. A turning point that electrified the entire scientific environment, giving engineers new motivation to design missions capable of reaching the nearest stars. The only and eternal problem remained that of distances, which, although astronomically small, were still too big for our technological possibilities. It would have served the discovery of a planet of terrestrial size, habitable, but also distant not more than 10 light years, which seemed decidedly difficult, given that the stars so close together can be counted on the fingers of one hand. But in April of 2016, astronomers came out with perhaps the most important astronomical news of recent years. Discovered in the habitable zone of Proxima Centauri, the nearest star to us, a rocky planet a little larger than Earth. It's called Proxima B. It was hard to believe, but a planet suitable to host life had been discovered right in orbit at Proxima Centauri, the nearest star to Earth. It was a dream come true at last. The little red dwarf is the third and weakest member of the triple system of Alpha Centauri, describing a very long eclipse that runs in about 547,000 years. Proxima orbits around the two main stars of the system, much brighter and more similar in characteristics to the Sun. Currently, it is close to the point of maximum distance from the center of gravity of the system, equal to about 13,000 astronomical units. The planet named Proxima B has instead a minimum estimated mass equal to 1.17 times that of the Earth, and orbits around its star in 11.2 days at a distance of about 7 million kilometers. This is a very small distance if compared with that of Mercury to the Sun, 58 million kilometers, or the Earth to the Sun, 150 million kilometers. This could make you think of a planet with a very hot surface, but Proxima Centauri, with a surface temperature of 3,000 degrees, has a brightness that is just 1/1000th of the solar one, so that astronomers have estimated that Proxima B receives 2/3 of the light that the Earth receives from the Sun, which is enough to ensure a surface temperature compatible with the possible presence of liquid water. In short, thanks to the strong motivations brought by the discovery of an extrasolar planet so close, the idea of reaching another star no longer appears as mere science fiction. In fact, a few months before the discovery of Proxima B, a group of entrepreneurs and scientists had already taken the first step towards a mission to the Alpha Centauri star system. We are talking about the Starshot Breakthrough project. The Facebook patron Mark Zuckerberg, Stephen Hawking, unfortunately recently deceased, and the two Nobel physics laureates, Stephen Chu and Saul Perlmutter, are just some of the minds that have made possible a project that will cost between $5 and $10 billion and will be funded with $100 million by Russian billionaire Yuri Milner. The goal is to launch in 20 years a fleet of small probes equipped with laser-propelled sails. The total cost should be around $10 billion, and the company would take another 20 years to reach Alpha Centauri. On the contrary, to reach Proxima B, since the destination was obviously and immediately changed after the discovery of the planet. But here is the mission plan. The launch. Breakthrough Starshot has as its goal the realization of a completely different type of interstellar probe from those conceived so far. All this is part of a mission where there will be a mothership capable of conducting in Earth orbit thousands of nanoprobes that will use the well-known solar sail technology to move. It's known for over a century that light carries momentum and can give a boost to objects, but the sunlight is not powerful enough to accelerate a probe up to Proxima Centauri. The trip would require a huge sail and almost impossible to control. So in the project, sunlight has been replaced by radiation from powerful lasers placed on Earth to generate beams of light so consistent that they blow into the sails for several minutes without interruption, long enough to accelerate them up to 60,000 kilometers per second. Nanoprobes. The microscopic Starshot probes will not look like anything that's so far launched in space. They will be in-practice chips as big as a stamp on which will be implemented and miniaturized batteries, sensors, and cameras. The chips will be mounted in the center of a square sail of 4 meters on each side, all for a maximum weight of about 1 gram. To maximize speed and minimize laser damage, the sail will need to reflect almost all incoming light. During the acceleration phase, the sail will have to remain extremely flat and actively detect, compensating them, the imperfections of the laser beam, so that the vehicle remains on the right course. Even a slight deviation in the initial phase could send it on a very different trajectory. However it is designed, the sail will have to be resistant. The 100 gigawatt laser beam will hit it hard, generating acceleration tens of thousands of times higher than the force of gravity that we experience on the Earth's surface. The Starshot mission is obviously all about quantity. There will have to be hundreds of thousands of small probes sent to Proxima B, about 10 a day, to compensate for the inevitable losses that will occur during the trip. The development of the probes will proceed step by step. The first step will be to build a prototype that accelerates to about 1,000 kilometers per second, less than 2% of the speed foreseen for Starshot, with a total cost between $500 million and $1 billion. The journey. The lasers will push for a few minutes on each sail to be accelerated, until each probe will have reached a fifth of the speed of light and traveled a couple of million kilometers. The next 20 years, the time it takes to reach Proxima B, will then be decidedly boring, unless there are always possible accidents. At this stage, the greatest risk will come from collisions with dust particles, hydrogen atoms, and other particles in the interstellar medium. To this must be added the danger posed by cosmic rays, atomic nuclei that whiz through space at speeds close to the speed of light that can damage electronics. Even without destroying it, a collision could send the probe off course. It will therefore have to have its own navigation and direction systems, powered by a generator capable of exploiting a radioactive isotope such as plutonium-238, in practice a nuclear battery. These systems will have to include a basic artificial intelligence that controls the position of the stars and adjusts the course using photon thrusters. The arrival. If all goes as expected, around 2060, the onboard computer of each of the incoming Starshots will wake up, contact Earth for periodic check of its status, detect that it is approaching Proxima Centauri, and prepare for the flyby. When the probe arrives at Proxima, there will be no way to slow it down. It will speed through the star system in about 2 hours. This is a challenge for the design of the measuring instruments. Experts agree that the highest priority will be to send photographs to Earth. It is estimated that even from a distance of an astronomical unit, a photo could reveal whether the planet is watery and green like ours or sterile like Mars, and it could also detect features as big as mountains and craters. A spectrometer on board could probe the atmosphere of the planet, if it had one, indicating to researchers on Earth will be the existence or not of molecules such as oxygen, methane, and more complex hydrocarbons, which are possible signatures of life. The instruments can also try to measure the magnetic field of the planet or other variables useful to find out if Proxima B has an environment compatible with life or much more hostile. However, no photo has ever been taken by a camera moving at 1/5 the speed of light. And to find out more, you'll first need to find out how to do several simulations. The cameras will have to rotate to keep the planet under observation. And on Earth, computers will have to correct image distortions caused by the effects of relativity and the change of angle and distance of the camera from the planet. Then there will come one of the most difficult challenges for Starshot, for which those responsible admit they have not yet found a solution: how to transmit data from Proxima B to Earth using a laser beam of 1 watt or less. Basically, we will have to invent a way to amplify the signal to make it detectable from Earth after a journey of 4.22 years. It is being hypothesized that the nuclear battery on board could power capacitors to make the beam as bright as possible, similar to a camera flash, and to further amplify the signal, the sail could perhaps be used as an antenna. But the problem obviously remains and does not seem easy to solve. Well, this is what we can report on the more serious mission proposal towards Proxima B currently under examination. The Starshot Breakthrough project is certainly much cheaper and technically feasible than the Cyclopean Daedalus project, but it is probably flawed for the opposite excess: too much simplification to remain within mass limits and almost no ability to really explore the planets orbiting around Proxima Centauri. If they ever manage to get close to the red dwarf, the nanoprobes will speed through its planetary system at over 40,000 kilometers per second without the ability to slow down and with scientific equipment reduced to the bone. It will be a great stroke of luck if the entire mission will give as its main fruit the blurred image, at most a few pixels large, of Proxima B or some other planet orbiting the red dwarf. Experts not involved in the project express a mixture of moderate optimism and skepticism. I think there are enormous challenges in increasing laser power and other essential technologies, says George Quarles, Director of Research at the Optical Society in Washington, D.C., but adding that with the right level of public and private funding for optical and materials science research, there will be a return on this investment. Others say that Starshot's minimalist approach has the merit of differentiating the mission from previous and less plausible proposals. There is nothing that I can see that is completely impossible in an obvious way, says Caleb Scharf, an astrophysicist at Columbia University. We are not talking about a big spaceship to send to another star. Others fear that the technological obstacles may prove impossible to overcome. I'm cautious about the short-term future of the project, says Bruce Betts, solar sail expert at the Planetary Society. Every single piece of the problem seems to be surmountable until you realize you have to cram everything into one small mass object. And even if some of the probes manage to get on Proxima B, according to Andreas Zielis, president of the Icarus Interstellar Space Exploration Organization, it is unlikely to provide any useful data. He has a very low probability, if anything, of being able to send a return image from Alpha Centauri, he says. That small spacecraft can't carry enough energy to transmit a signal back. But as any explorer would say, nothing is better than to verify on the spot. In 2015, for example, Pluto's flyby revealed mountains of ice and nitrogen glaciers that were invisible to Earth's most powerful telescopes. Likewise, Proxima B, like every other exoplanet nearby, can hold surprises that will only be visible in a close encounter. There will also be more far-reaching returns, say mission supporters. I see Starshot as an opportunity to develop our capabilities, says Kelvin Long, Director of Interstellar Studies in London and member of the project's advisory board. It will be like when we went to the moon. Not to mention that a laser array capable of propelling a spacecraft to Proxima Centauri, says Long, even if it fails, it could easily send probes throughout the solar system in a few days, or into interstellar medium within a week or two. Wouldn't it still be worth a try?